Well, this is a very tempting formula, except that we haven't defined conditional mutual information. So I'll do that here. Definition. I of x, y, given z is equal to h of x given z minus h of x given y and z. Recall, over here, recall, I of xy is h of x, entropy of x minus the conditional entropy of x given y. So this is just the same thing as this, but I've conditioned everything on z. So if I have a joint distribution, P of x, y, z, I can define this way in parallel with this definition without the conditioning. Then with that definition, this becomes true. Good. Now, the mother of all the inequalities is not that the entropy is positive, non-negative, or that the mutual information is non-negative, although those are both true, and entropy is positive in the discrete case, but that the relative entropy is positive. So, we have the relative entropy, dpq, where p is this vector, well, p1 through pm, q is some other vector, probability mass function. The pi's are non-negative and sum to 1, and so do the q's. And the QIs are non-negative. All right, great. So this is summation pi log pi over qi. Again, what's the base of the log? Most of the time we'll be using log to the base 2, but occasionally we'll use the monotonically related, just by a positive multiplicative constant, log to the base e, because certain things are more because we don't need to keep track of that multiplicative constant when we use, say, Jensen's inequality. All right, now, for this, we need some conventions. We need the fact that, say, 0 log 0 over 0 equals something. P log P over 0 equals something. And 0 log 0 over Q equals something. Well, if we look at P log P over Q and use simple continuity, we get 0, infinity, and 0. So this is now well defined, even though, say, P and Q have different support sets. What's a support set? It's a set of indices for which P is strictly positive. That's a support set of P. Right. Now, we'll look at convexity. And a convex function, f of x, is convex if, well, the second derivative is greater than 0 for all x. Convex over the set, say, A, for all x in A. Now, wait a minute. There's some nice examples of this, and then I'll give you the wait a minute. F of x is, say, x squared. That looks like this. Or e to the x. That looks like this. Or x log, is it 1 over x? No, well, x log x. I think that looks like that. Or log 1 over x. And that looks like whatever it looks like. Okay. Now, also, this is a nice convex function. But notice it's not really twice differentiable. So I've really just specialized the notion of convexity to when it's twice differentiable. The all-encompassing definition is f is convex over A if lambda f of x1 plus lambda bar, that's 1 minus lambda, f of x2 greater than f of lambda x1 plus lambda bar x2 for all x1, x2 in A. In other words, if the curve f of x lies below the chord joining any 2 points in the curve. Actually, a convex set is one that contains all the chords joining 2 points in the set. So the wait a minute was, I wanted to include things like this too. This is the definition that encompasses them all. And a definition, f is concave if minus f is convex. So, example, f of x equals log x. Great. And that looks like this. Okay, let's quickly prove Jensen's inequality, and that's from that, everything good will happen. Jensen's inequality. If f is convex, then the expected value of f of x is greater than or equal to f of the expected value of x. So I better say that x is a random variable. This is for any distribution on x. F is not the underlying distribution, it's just some function, a convex function. All right. What that means as a picture is just this. Here's a convex function. Here's a distribution on x. Here's its mean, mu. And that is the point f of the mean mu. Mu is the expected value of x. And it just says that if I average these values, I get a point greater than f of mu. The expected value of the function is greater than the function of the expected value. Okay. Notice how much it looks like the formal definition up there. But that's just for two mass points, and this is for an arbitrary distribution on x. Okay, the proof if it's twice differentiable, the proof is easy, and the details when it's not are easy too. But let's just do it assuming twice differentiability. And so we do Taylor series with a remainder. F of x is equal to f of x naught. So here we have our curve. Here's x naught. Here's f of x naught. And I'm going to draw the tangent line through that point on the curve. So f of x equals f of x naught plus x minus x naught times the derivative f prime of x naught plus x minus x naught squared over 2 times f double prime